set up the UPA1 boring head with a small carbide boring bar, and well, we're just going from 9 to 10 millimeters now. Let's get a gauge pin in there. Okay, 9.8, 9.85. Yeah, 9.88. Okay, let's do a spring pass, and instead of hand cranking my way out of the bore, I'm going to use the power feed to do a spring pass on my way out of the bore. I don't want to use the power feed into the bore because it's blind hole, and I don't want to run the boring bar into the floor or the face down there. Okay, 10 millimeter, and I probably overshot by a lot now. Okay, 10 millimeter pin. Woohoo! Oh wow. Oh yeah. I'm always the guy who don't do that. If you have to force the gauge pin into a bore, it's tight. But I'm going to leave it because the mating part is tolerance minus 20 microns, so it will fit anyway. It would be nice if the bore had a flat ground, which an end mill doesn't do. End mill leaves a 2-degree dish to the center, like a dome in the center. Using a permanent marker and compressed air to blue up the inside of the bore. And now I'm going to use the facing function of the boring head. It means I have to disengage this pin here and engage the power feed out here. Now when it spins and I hold this upper ring, the boring head will feed itself while it's rotating outwards and do a facing cut. I undercut the wall a little bit, disengage the power feed, and retract the tool. There we go. That's our 10 millimeter precision bore with a truly flat floor. Next we can cut our large 16 millimeter radius. For that we need to get this point here to spin on the center of the indexing head. See, when I rotate the indexing head now, this point here moves somewhere, completely out of whack. We move the cross slide until we get this on center of rotation. I will get an indicator in a second, of course. For now I'm just rough moving it to where I think it should be. And as you can see, this is a fairly heavy duty made with large dovetails down here, so you absolutely this is absolutely made for milling. This is an absolute nicely made item. When you indicate something on a rotary table, you have to think about what you rotate. Do you want to rotate the spindle of the machine? Then you're locating a feature on the rotary table. Or do you want to rotate the work with the rotary table? In this case, I want to move the work to the center of rotation of the rotary table. So it means I need to spin the rotary table to get to my center. That's fairly easy. So I'm using the mill as an indicator stand now. So when I get my indicator here to 0 and I do a full 360 spin, this is not too far off. -10, -20. And it's going back to 0. So I think this is good enough for the purpose at hand, which is cutting a radius, a cosmetic radius on a part. Let's lock the axis of the compound slide. And now it would be nice if the mill spindle was also directly in line with the center bore, which is also the center of rotation of the indexing head. This just makes adjustment later easier. So let's dial that in too. We do this by spinning the dial test indicator with the machine spindle. I'm not getting overly concerned about the precision here. Yeah, this is within 10 micron. That's fine. You're probably thinking now, wow, Stefan got this fancy XY compound slide on his indexing head, so he can cut this feature. But you can also, there are 1,000 ways to do this. This is just overcomplicated way that's nice to look at for YouTube. Also, I wanted to do it with this tool because I never used it before on a real part. And I want to get some practice if I ever need to do this, because we got struck by a solar flare and all the CNC machines crapped out. And I will have a machine shop that's still operating. Now we think what we do, we have everything aligned. Now we can get rid of our helper block here. And now we have all the space in the world to machine our radius. As you can see, I nibbled away most of the material just by going straight lines, and now I'm moving in the X direction to get to my desired cutting diameter, which is 32 minus the cutter diameter divided by 2. I used the roughing end mill to get within 0.5 millimeters on depth and radius. So let's clean this mess up, change to a finishing end mill, and finally end this part here. Okay, there we go. That's our radius. It was a lot of setup for a seemingly simple feature. And as I said, if this was a CNC part, this radius would be a no-brainer. Would be super easy. Same for the precision counter bore here. Just helical interpolate it, check, and be done. But on a manual machine, it's a little bit more effort to do features like that. But I don't want my parts to be super simple plates with holes. We have enough of that engineering already. So here's the finished product. Needs a very good deburr, some Scotch-Brite work, and it's almost done. For the next part, I already have sawn off a piece of Tulox 33 and milled it on two sides to dimension with grind allowance. But the ends need to be squared. On the last part, we just held it out here in the vise and side milled it, but honestly that's bad practice with such a short part because you're racking the movable jaw of the vise a lot. You could put in some packing here to make up for that, but there is a technique to square the ends of parts like this without having to do damage to our vise or find some packing. It's just one step more, but I will show you. Just put the part in the vise kind of squarish. Doesn't need to be square. Just put it in, and you want it to be in the jaws relatively deep. Then we just face mill it. Yeah, that's a little bit much of an angle because we were losing a lot of material that way. I cut it with relatively little allowance. Okay, just eyeballing it square. Okay, we need a marker. This is the first side, and this rear side was back up on the jaw. Now we can take it out. And what did we achieve now? Well, not much. It's far from square. But haha, let's look in the other direction. Aha, it's square because we used in that orientation the back side of the jaw as a reference against the workpiece. Now we take a very shallow parallel. Well, should be enough to clear the top of the jaws here. And this direction is not square, so we cannot rest it on the parallel. But if we use this side on the parallel, it will be square. You might also notice that on the previous cut the part moved on me because I didn't tighten the vise. You want to make sure that it's seated down on the parallel. Okay. And now this side should be square on two sides. This also works for parts that are so large that you cannot side mill them out the side of the vise. You of course are limited in length of the part because you can't have like 200mm stick outs on top of the vise. But that's the reason why we learn different techniques. Okay, second side, inspection. Square. And square. Now we just need to deal with the other side, clean it up, and we're good to go. Okay, didn't clean up completely here because when I cut the first surface, the part was very much on an angle. To get a rough alignment on the very first cut, you can put up a square or a 1, 2, 3 block. But I did want to show it at an extreme angle so you see that you can generate squareness in the part without any squareness reference or doing side milling. Okay, squaring up the part on the grinder means grinding two sides parallel on the magnet. And sometimes it's best to tear down the setup completely and just start from scratch from a clean magnet. So now we grind it down to 15 millimeters. First two sides ground, and we should be close to 15 millimeters. And as I said, this is just so we have an easier life when we do mill work. Having a very nice square block to begin with makes everything easier. So now we get our good grinding vise on the table. We need only one parallel here. The two parallel sides align the part well enough. And I let the part stick out to the side of the vise, despite what I said earlier, that this is bad for the vise, but I'm clamping on it very lightly because we're here on the grinder. And that way I can do a third side or the face of the part without having to reclamp the vise. So grind this side so it's square to the two parallel sides, and then we grind the face here and deal with the other side on the magnet. Okay. Clean off the magnet. Drop the vise sideways on here. Now we can very carefully hit this side. Okay, now we have three sides squared up. This is the side that didn't clean up from the milling completely. We will see how much we have left later after we squared the other side, and then we come back and grind it to final thickness. Little oops on my side. But not everything is perfect, so I'm fine. Let's grind the 17 millimeter dimension first. Block it in, just putting a block behind it so it doesn't skid off the magnet. Little trick, if you leave the parallel hanging over the magnetic chuck back here, it's easier to get off without scratching the entire magnet when you try to move the parallel off the magnet. You can just pop it loose by lifting it. And pop the parallel loose without sliding stuff around. Trying to do as little sliding with freshly ground parts on a dirty magnet as possible. With a freshly stoned and clean part, it's a different story because it's clean on clean. That usually doesn't leave scratches. But right after grinding with burrs and the abrasive grit from the wheel and the swarf from the part, sliding the part around will scratch the magnet and the part. I don't say it doesn't happen to me, it happens a lot to me, but I try to not do it. These small Moore setup blocks will serve very nice to block the part in. And just for good measure, I'm adding a second block in front here, so nothing can happen. This is a very safe setup that way. Okay, cleaned up this side, get off our rear packing block, get off this one, and clean off the magnet as good as possible. Okay, part is in place, and we add the rear packing block too. Now we can grind it to final thickness and hope we don't leave much of this unground surface. Okay, there we go. It didn't clean up completely, but I'm pretty confident that I can hide this on the final part. So 6-side square and to dimension. Deburr it and over to the milling machine. Looking at the drawing, which is very confusing for if you see it the first time, down here we have an isometric view of the part. It looked like this. We have to do a very large cutout here at an angle with a small dovetail feature in here, and the back side of the part gets a key, and the key slots into the 6mm slot in the main body of this tool. This area here didn't clean up completely, but I decided to have it on top and facing towards the dial test indicator so I can just grind a little chamfer here and make it invisible. So we go to the mill and we'll just rough this out with an end mill. Also finish it. And then we have to tilt the vise by 12 degrees. Well, I have to check the angle. It's the angle of this dovetail on a dial test indicator. I don't know which angle this is. So we have to measure that before we do anything else. Well, we can rough it out square. Then we measure the angle and then we cut the angle. Then we reset up and we cut the dovetail. Also we can do the setup, the 2 holes in this part. And I scrapped it. I'm in the wrong orientation. The part is off by 90 degrees. It would need to be, the 17 millimeter dimension needs to be standing up, not lay flat down. And that happens if you don't think along and do wrong sketching. It would need to sit like this in the vise. Now I don't have material for the key on the back, so this goes in a scrap bin, and I will cut a new piece of stock. And there would probably some way of fixing it and saving it, but to be honest, there is not much work in it at this point in time if I don't have to film it. And back with a new piece of stock. Things like that happen if you are not 100% focused on your work or do constant checking back and forth. I can excuse it by doing filming at the same time I'm doing the work. Okay, back to square one on this part. I squared up a new piece of stock. I'm holding it in the vise in the right orientation this time, and I already hogged out most of the material. And I'm just checking if my dimension here is good. And this, it should be 12.5 right now, and it's 12.51 according to calipers, so well, it's fine. Okay. Also, let's check the depth of the step. It's not really a mission critical dimension, but I want this to resemble my drawing as reasonable close. Target dimension is 11.5. We're at 11.09 right now. Okay, 11.507, that's fine. Since I didn't know the exact angle that this front portion of a DTI has, at least on these Martest 800 is what I'm using here. Didn't know the angle, so I put it on my scissor type sine bar, a magnet on the back side, because the DTI is non-magnetic, of course, and using a can twist clamp to clamp the DTI to the magnet. And I just added gauge blocks down here until I got on the dovetail up here on the DTI a reading. So kind of 0, 0. There's a little mark from one of the clamps that holds it in place, but that's close enough. So now I need to figure out the angle from the gauge block stack. So my gauge block stack is 12.7 millimeters. So we need the inverse sine of 12.7 divided by the distance of the pins on the sine bar, which is 65. And we get an angle of 11.26 degrees, which is, well, up in the office with a drafting triangle, I measured 12 degrees. Down here with a universal protractor like this, I measured 11 degrees, and to be honest, I trust the sign bar the most. 11.26 degrees. Off camera, I drilled and counterbored and tapped these two holes. The lower one is to hold this clamp to the main body, and the upper one will be there to clamp the dial test indicator to this block. It's drilled clearance in the upper portion and then threaded M3 down here. The middle section will be slit. Let's rotate this by 11 degrees so I can cut my angle. And now I just need to cut parallel to the x-axis to get my chamfer on here. Good old 6mm 4-flue carbide end mill. I could save the world with a 6mm end mill, to be honest. Best end mill diameter that's out there. How far did I cut? Well, I put a scribe line here measuring from the outside to here, which gives me the theoretical sharp corner of this feature. That's just a drawing dimension. It's not super critical, just cutting to the line with some magnification for inspection is perfectly fine. I stayed clear of the bottom surface, and I will just glue that up now. And I will very carefully blend those two surfaces together. I could do it on the surface grinder too, but I feel like milling today. Okay, my last down feed was 5 micron, and that's small enough of a step so it will just polish out by hand without much effort. Using an 8mm end mill to cut the key feature on the back side of the sliding portion of the dial test indicator holder. After roughing the key out, I'm using smaller and smaller incremental cuts to sneak up on the width of the key, and I'm using a disc micrometer to verify the width of the key. A quick word about disc micrometers. They promise a solution to a problem, but they absolutely under-deliver. Since you're measuring off-center to the line of the force on a micrometer, the reading is extremely depending on the skill and your placement of the micrometer. It's super sensitive to tilting. If there's a little bit of wear in the micrometer itself, the reading doesn't get consistent anymore. They create a whole lot of different problems. It's a fairly rough inspection tool, despite looking like a micrometer. But here it went quite well. but I'm also using the real part that will fit onto the sliding part as a hard gauge. In this case, this is a better solution. And you want this part to be a tight sliding fit. It shouldn't rattle around, otherwise adjusting it will be a little bit annoying. Just saw me milling the key feature on the back side of this part, and I made it a very tight sliding fit in the body here. So it barely wants to fall out. Gets a little bit tight to the end. That's most likely due to the slot in here, giving the part a little bit of elasticity here in the center. But I will stone a little bit of the slot out here on the end. Looking good so far. I really like it. Feeling quite confident. And when I take a dial test indicator, and now imagine the dial test indicator sitting in a dovetail down here, we get an idea of how it will look. This is the all the way closed position with the stem or with the probe of the dial test indicator almost in line with the shank. Dial test indicator following the line, or the body following the line of the dial test indicator bezel around here with the radius. I will most likely radius this because it's a little bit sharp here. You can't cut yourself in CAD, so that's that. But so far I like it. Okay, I clamped the part in the vise and I adjusted it with copper drift until the surface where the dovetail will sit in is level with the X travel of the machine. Means indicated I lightly tightened it and just bumped it around with the copper drift until I get a reasonable small reading on the dial test indicator here. I think I have shown that numerous times. Edge finding, then roughing out the slot, finding a small dovetail cutter and cutting the dovetail. Business as usual. You see me usually using either one of these edge finders or a dial test indicator to pick up origins of workpieces. I also have one of these. And careful, incoming rant. It sucks. In all honesty, it's not a nice tool. It has an extreme high actuation force compared to a dial test indicator. It doesn't instill any confidence at all. The adjustment for run out is super squishy. It doesn't feel like you are in control. You are not. You're hoping that you get your run out true when you adjust the shank to the probe. I don't even put it in a dedicated 40 taper holder anymore because I don't use it. It's really a bloody annoying tool to pick up origins. It's fairly expensive. It takes up a ton of C height. It requires 100 millimeters from the spindle, from the back of the housing, plus whatever tool shank you have, like a 40 taper weld-on. I really don't like them. They don't hold their zero if you mildly put them away a little bit harsher, like setting it on the table. They tend to drift away. I'm really not happy with them. The actuation force is different if you go X, Y, or diagonal. And overall, listen to it. I get it up to my microphone. It's just not a tool that instills any confidence in picking up workpiece origins. And picking up a workpiece origin is most of the time very important for precision on a workpiece. Granted, these are fast. You see what's going on. It's extremely fast tool, and many people like them for that, but I don't trust him for any precision work, and that's why it's sitting on my shelf 99% of the time. Rant over. So that's why I like these. These are independent from runout. You can put them in a drill chuck and still get the same precision that you would if you put it in a collet. They are simple, they are very cheap. A good one is like 50 euros. You can buy a cheap one and tune it up to be as good as an expensive one. They're reliable, they take up very little sea height. You can get them in different shank diameters. I have one with 6mm shank for the CNC. It just works. Same for dial test indicator. This is a super versatile, highly precise instrument, and with some practice it's very fast. And the tool we're building here will make it even faster and more convenient. So that was my rant of the Monday. Yep, it's still Monday. So let's find an end mill and rough the slot out. Using a 4mm 4-flute roughing end mill, well, it's a carbide HPC roughing end mill with smooth flutes. This cutter could cut the slot for the dovetail in one pass, but I came to the habit of cutting slots with small end mills more in a high feed approach, like taking a fairly shallow cut but feeding relatively fast, especially on small parts like this. This doesn't add much time on the machining, but it's easier on the machine, it's easier on the tool. Yes, you wear out the end of the end mill faster, but on good end mills for steel machining, you have about a 0.2mm wide edge chamfer on the end mill to protect the front. And when you stay within those 0.2mm depth of cut, the cutter lasts basically forever with this strategy. I use the same strategy on my CNC router, and it's extremely effective. Once I'm to depth, I'm just stepping over to cut the slot to size before I cut the dovetail profile into it. This is the tiny 60-degree D-bit that I'm using to cut the dovetail for the dial test indicator. I ground the D-bit years ago on the single flute cutter grinder, on the D-bit grinder, and ever since I used this cutter to make dovetails for dial test indicator clamping slots. I think I showed grinding it in the video where I made the squareness comparator. If you don't have a D-bit grinder or a surface grinder with a spin fixture to make this tool yourself, such a small dovetail can easily be filed with a triangular file. People who do the gunsmithing do this all the time to fit sights on the slides of pistols. They just use a 60-degree, well, any triangular file is 60 degrees. They use a 60-degree file to go from a square slot to a dovetail slot. I've done it too. It can be done. It takes a little bit of skill and practice, but also this is just a clamping slot. It's not a moving dovetail, so the precision requirement here is medium at best. I'm running here at 2000 RPM, and a little bit more would be nice because it is a single lip cutter and the feed per tooth is relatively low, and since it's only one flute, you can only feed relatively slow. But with a little bit of patience, works quite well. You can also purchase real small 60-degree dovetail cutters made out of carbide with 2, 3, or 4 flutes in that size. Those would work probably even better. And here is the final fit up with the dial test indicator. Tiny bit of wiggle, but as I said, it's a clamping slot. You need some room to get the dial test indicator in and out. using a 1mm slitting saw here. This is way too fine of a tooth count, but I didn't have another one in this size. In reality, a coarser blade would work better, but when you take shallow passes, you can make a fine tooth saw blade work on deep cuts too. The problem is that the chip will fill up the gullet of the teeth very quickly if you take too deep of a cut, and then you run in all sorts of problems like blade deflection and the blade seizing up because you try to push a chip into the gullet, but the gullet is already full. Then you create heat and friction, and in the end you have saw blade segments flying through the shop. Got it all together, but it's super sharp edged and there are a million corners to cut yourself and scratch yourself open. So this needs a ton of deburring and corner rounding before we can call it done, or before we proceed anyways. So now the test indicator is clamped here very nicely with the dovetail. It's worked out perfectly fine. This is the clamping screw. The screw that holds the slider to the body itself has a nut on the back. I will make a knurled nut, of course. But the screw is captive in the slider part here just by means of threading it in. That's a very simple solution to get a part with a thread stud sticking out on the back. So this needs some work. And I also, off camera, I turned the shank. So as you can see, the shank is offset. The 6mm diameter here is offset by 0.5 millimeters, contrary to the drawing I did where the offset is 1mm. I moved it off center by 0.5 just by putting in a little shim in the chuck. There's an M3 thread in here, so this goes in here and gets screwed in from the underside. And by spinning it, you can adjust to get, wait a second. To get the probe tip in line with the center of the shaft. And that's very important for indicating small diameter bores or bosses. That's a little feature that I wanted to incorporate in my design. And when I redesign this style of indicator holder, I will also incorporate a off-center feature up here. So yeah, this needs deburring, chamfering, rounding over. And also, somebody on Discord mentioned it would be neat to have some kind of a handle to spin it, so you don't have to touch the body of the dial test indicator. I found a 16mm ball handle in my collection, and we will just put a maybe 20-25mm long shank in here with the ball here in the end. Will be removable if I don't like it, but I think it might be useful to have something to grab on, especially when it's oriented away from you. So that's one little thing that I want to add. But first, deburring. Yeah, I could do the chamfers on a machine too. But sometimes I like to do some bench work. I'm starting with a 0.25mm chamfer on all exposed edges for now, and I will go from there. And before we proceed on with sending it out for plasma night writing, you want all machining to be done on it. Often I use the vise for deburring just like a cradle for the part, so it doesn't slide all over the place. Up on my project list is an engraver's vise, a ball vise. If I can get an ancient cannonball to build the ball section of it. So all the edges are chamfered now, except for the inside here. I will do those with a die grinder, but right now I'm in filing mode. So next thing is to ball over all the corners. For that I usually file like a compound angle chamfer onto the corner, bisecting all three adjacent surfaces. Just like this. And then I just ball it over with three motions, with each of the three surfaces as a reference. One time referencing this one, going in radius, top one going in a radius, and the rear one going in a radius like this. This usually goes better without a vise. Just right here on the bench, or even better on the edge of my workbench. That's usually my preference here. Or my bench vise as a cradle. Here I can just put the part up against, can do my compound chamfer, do one round over, two roundovers, and the third one. And the result is a nice fold over corner that doesn't scratch me open when I run my hand over it. I don't like sharp cornered chamfers on tooling that you're handling day in and day out. Oh boy, are you dragging your file? Oh yeah. Sometimes I'm not. Depends on my mode of operation with the file. So that's getting very close to what I want. Now we need a die grinder and a small triangular file for all these internal features. And then we proceed on to this, and we put it together, surface grind some surfaces in an assembled condition, so we have nice flush surfaces. I think I got most of the parts finished now. I also made a knurled nut from stainless steel, just with a straight knurl. So let's put this together. Long screw goes in this slider block, screws in all the way. On final assembly, when it's back from heat treat or from night riding, the screw will get Loctited in, so it's securely in there. Goes together like this. Slide needs to be clean. This needs also to be clean, so we don't rub abrasive grit into each other on these parts. Nice free sliding. The nut goes on here. Since it's a nut that's used very often, we put a little bit of molybdenum disulfate grease on here, just to prevent fretting. And I made it on purpose with extremely long thread engagement, so when you loosen it, it doesn't feel wobbly at all. Very nice positive lock up here. Probably going to make a hardened washer too, to go between the screw and the slot. But for now, just for testing, this is fine. The shank goes in here. We just finger tighten it for now because we still need to adjust it. Last screw goes in here, and this is to clamp the dial test indicator. So I dug out my better MAR 800S. Goes in all the way. And we carefully tighten it in place. And it's tight. Okay, there is our little indicator holder with an extremely low profile. Another thing that I want to do is, currently I'm holding my dial test indicator in a ER20 collet holder, which is relatively long and also relatively expensive. I also have this 6mm weld-on HSK holder, which I want to cut off about here with an abrasive wheel, then drill and tap a new hole into it. So I get about this length overall for the dial test indicator holder, which is fairly low profile, to be honest. Maybe I'm going to make a second one for the manual machines that I have, but this one will live on the CNC. I like the stainless screw over here. I didn't put a fine adjust in. My very first iteration of it on paper had a fine adjust, but that all got extremely small and very, yeah, just a tiny screw here. Didn't look too promising. So I went without fine adjust. I think it will work out. So there it is. Let's put it in a machine and see how it behaves. One last addition is this handle here. This is just a piece of stainless steel, tapped M4 on both sides, and with an off-the-shelf plastic ball handle on one end. I prefer to make studs like this by tapping and screwing in a set screw. At final assembly I will glue the set screws in, and it's just faster than turning OD, doing an undercut, and then use a die or a threading inserts to cut the thread. Just screwing in a hardened set screw is usually faster and gives you a nicer result in general. So this goes in here, and it's fairly well balanced size-wise. It's hanging over 60mm on this side, and also about 60mm on the other side with the handle. I already put it in a HSK 32 weld-on tool holder to go in my CNC. Okay, we're over at the CNC mill. Let's put it into the spindle. And pick up a bore. There are different techniques to center up on a bore on a CNC mill, but if you have no clue where you are, a averaging method works very well. So you go to one side of the bore, for example at 3 o'clock, you zero out the DTI in one position, zero out the DRO in the same position, spin it 180 degrees, go to the other side, also to 0, and you take your value on the DRO and split it in half, so I have to go to 2.8. So then you go 90 degree, to the same, the opposite orientation, 3.2, 1.5. So now you're roughly in the center of the bore. Now you can adjust your indicator out to make contact with the bore to somewhere and zero it out. And now you can start to sweep the bore. So we have -8 here and 0 here, so we have to go to -4, zero it out, Y direction, go to 0, 0, there is some crud in the center bore of the pallet, but well, that's 0 with 10 micron deviation all the way around, and I really like it. It's the adjustment here with the on this to get the dial test indicator into position is fairly nice, and once it's roughly in position I can use the dial anyway to zero it out. So I think I get along without having a fine adjust. So I have to say I think I like it, but time will tell me if it's a good idea or not. So then we have picked up our 0 and we take it out of the spindle and we change to a real tool to do some machining. I moved the indicator holder over to the FP1 because I can film easier on here, and now it's a matter of adjusting the dial test indicator tip, the ball on the end of the stem here, to be in this orientation centered to the center of rotation of the machine spindle, and for that we have the eccentric up there. The only thing that I overlooked when I designed it is that you have to be able to reach in here with an Allen key to loosen the screw. Do your adjustment. Note that I'm spinning it with the machine spindle standing still. Means I'm adjusting the eccentric right now. So let's go to a 90 degree extreme and show you what I mean. On the FP1 I don't really need the handle here because the machine has a hand wheel on the back where you can very conveniently spin the machine spindle with the machine being in gear. So let's see, we're at the 90 degree orientation here, and let's see what happens. And the ball of the indicator is kind of on center with this carbide tip in the machine vise. Right now the ball of the indicator tip is kind of on center with this carbide tip in the machine vise, and let's see what happens if I spin it 180 degrees. This will tell me if the ball is on center line with the machine axis. So let's spin it 180, eyeballing is good enough, And it's not at all. Also the stem or the tip here of the dial test indicator is bent. Somebody has crashed it in the past. Could have been me. Okay, and the idea to adjust it is you loosen the screw in here, then you go a defined direction like clockwise, and let's try just 1/8 of a rotation and do the same test again. Takes a little bit, but I think that's a okay way to adjust it for center line. Lined up again, spin 180 degrees, and I think it got worse. So let's go 1/8 the other direction. Okay, lined up, spin it 180, and we're getting better. Let's do another 1/8 of an rotation here. You need to do this adjustment once for a certain dial test indicator. You don't swap out dial test indicators in this holder after you adjusted it. Okay, get it on center line again, spin 180. That's darn good. I would say I'm gonna leave it like that for now. And now you can just use it as you want. Of course, you tighten down the adjustment screw in here finally. In here with an Allen wrench. Just so you don't accidentally spin it off center. And you need the center adjustment for indicating very small holes, or for example here on this taper. Like this. Also, edge finding with a dial test indicator is way easier if the tip of the dial test indicator is in line with the center of the spindle. Like finding the edge here, getting it in contact, finding the high spot, zeroing out the dial test indicator, zeroing out the DRO of the machine, spinning 180 degrees, dropping down a little bit, moving in a little bit, using a ground block against the surface we want to edge find, get it to 0, find the high spot again, zero out the value on the DRO and crank to 0. And now the line of the spindle, the center line of the spindle, is exactly above the vertical extension of this plane. So that's the idea behind this holder, and using it I'm very confident that I'm going to make a second one for the manual mill. But Stefan, haven't you heard of coaxial indicators? Yes, I have. I own one. Honestly, I don't use it at all because it takes about that much C height, and it doesn't instill the confidence and precision that a dial test indicator does. It has a lot of moving elements in addition to the indicator that's mounted to it. A dial test indicator is bare minimum. Everything else, the holder here, is so rigid and so solid that there is no additional error introduced. And let's not talk again about these because, so for me, the two important measuring tools on a milling machine is an edge finder, preferable two sizes, 6 and 10 millimeters, and a dial test indicator in whatever holder you can cook up. This new low profile holder that I built, I will see if I like it. This style of indicator holder, which is also shop built, I like a lot. Some people like a flexible Noga style arm like this. These have their advantages, but they also can be a little bit tricky to use. So generally I prefer to avoid them. That's my 50 cent on indicating in features on milling machines and building this tool. So I will have a link down in the description to the PDF file for this dial test indicator holder. I will do a revision of the drawings, and the video should be enough of a manual to build one yourself if you want. Thank you all for watching, and thanks for the support. The support is honestly a part of why I can keep this channel free of, well, this video is sponsored by WD or whatever. By having this fairly good sized chunk of money coming in, I can bite away time from working on customer projects to do small shop projects and also document customer projects here on the channel and keep all the content free for. Hope you enjoyed. Thank you all for watching. Thanks for the support, and I'll be back.